Hello, and welcome to the analysis and design of power electronic circuits. My name is Marcelo Perez, and today we will review different models for voltage source converters. There are several models in power electronics. We will focus only on two. The switching model, which considers the commutative behavior of devices and is useful for numerical simulation and component design. And also the average model, which is useful for mathematical analysis and control design, but it doesn't take into account the commutation of the devices. Today we will model the three-phase voltage source inverter you can see in this picture. This this converter has the same structure that other converters we have seen in previous lectures. It has the power source, it doesn't have the input filter, it has the power converter, the output filter, and the load. The power source is defined by the voltage. The output filter and the load, they are modeled together, and the converter is modeled using its switching behavior and then introducing the modulation to obtain the average behavior. We will start modeling the output filter. Formulating the voltage equation, we have the phase voltage is equal to the voltage drop in the inductance, the resistance, and the neutral voltage. For phase B and C, we have the same equations. And also, in the neutral point, we can formulate the current equation. To integrate these four equations, we add up the three voltage equation, resulting in this expression, and recognizing here the summation of the currents, which are zero, we can then solve for the neutral voltage, obtaining a combination of the phase voltages. This voltage is also known as common mode voltage. Replacing the neutral voltage into the dynamic equation, we have this set of equations, which can be written down in vector notation. And you can here recognize a matrix. This matrix here we will denote it as Q and has some interesting properties we will see later. The model of the output filter then is this equation here, where the dynamics of the current is related to the voltage. We will continue with the converter model. We developed this model using the basic switching unit you can see here in the picture. It has two devices which are commanded by only one switching signal. This signal can have only two values, 0 and 1. When this switching signal is 1, the upper switch is on, the lower switch is off, and this point is connected to VDC. On the other hand, when this signal switching is 0, the upper switch is off, the lower switch is on, and this point is connected to 0. If we combine these two behaviors into only one equation, we find that the voltage, the output voltage, is equal to the DC voltage multiplied by the switching signal. And this is also valid for phase B and C, and can be written in a simplified way using vector notation. The output voltage of the inverter has the same waveform than the switching signal. As you can see, multiplied by the DC voltage. In this case, the output voltage goes from 0 to 500 and it has a DC component. If you consider the effect of the neutral voltage, then you can measure the voltage referred to that neutral. And the output voltage now is a combination of the three switching signals, as you can see in the last figure, and it has an alternating behavior and no DC component. This voltage is the one that is employed to generate the output current, as you can see in this model, which is the switching model of the BSI. To obtain the average model of the converter, we have to integrate the modulation. In this case, the modulation is considered as three modulating signals with the same amplitude. These signals are compared with a triangular carrier to generate the switching pulses. This modulation then is an interface between continuous modulation indexes to discontinuous switching pulses. But these pulses must keep the main features of the modulation index. That means the amplitude, the phase, and the frequency. To find the relationship between the modulation index and the switching pattern, we calculate the average of the switching pattern in one switching period, just like you see here in the figure. Using the mean value equation, you can find this expression for the average value. And if you notice here is the on time divided by the switching period, which is similar to the duty cycle in the DC-DC converters. But in this case, this duty cycle is variable. Calculating the point in which the carrier is equal to the modulation index, we can obtain the expression of T1 and the expression of T2, and then replace them in the average value of the switching signal. We can obtain this expression. And what this expression means that the switching signal has a DC component, a fixed DC component of 0.5, and a fundamental, the half of the fundamental component of the modulation. We can verify this by taking the frequency spectrum of the signal, and we can actually see that the DC component, a fundamental component with half the value of the modulation index, and then the switching frequency. We are taking the average in one switching period. That's why we cannot see these harmonics in the expression of the mean value. And of course, this is also valid for phase B and C. And in a more simplified notation, we can write down this expression for the mean value of the switching signals with the vector P, which is only 1, 1, and 1, and the vector of the modulation indexes. Replacing this switching expression into the switching module, we can obtain this expression for the output voltage, which has two terms, one related to the multiplication of Q by P, which is 0, and Q by M, which is only M. So the average model results in this expression here, in which all the variables, the current and the modulation index, are only sinusoidal signals. In the figure, you can see the difference between the switching model and the average model. In the switching model, you have commutative values for the output voltage and current with ripple, because the inductance and resistance react to these changes in the voltage. In terms of the average model, you have only sinusoidal voltage at the output and also sinusoidal current. As a summary, we have obtained the switching model of the converter in which the inputs have only two possible values, 0 and 1, and all the variables have react to that dynamic. We have obtained then the average model in which the input is now a continuous signal, a sinusoidal signal, and of course the current is also sinusoidal. And of course, if both are sinusoidal, then we can apply phasors on them and obtain the last expression here, in which you can calculate the amplitude of the current and the phase of the output current. So that's the lecture for today. Thank you very much.